Errors and exceptions. Until now, error messages haven't been more than mentioned, but if you have tried out the examples, you have probably seen one. There are at least two distinguishable kinds of errors: syntax errors and exceptions. Syntax errors. Syntax errors, also known as parsing errors, are perhaps the most common kind of complaint you get while you are still learning Python. And as far as I can tell, people still make them whenever they've learned it already too, so don't feel bad. For instance, say we tell the interpreter, while true, print hello world. Now this seems pretty innocuous, but this hypothetical person pressed enter and got this back: syntax error, invalid syntax, with all these little arrows pointing at print. The parser repeats the offending line and displays little arrows pointing at the token in the line where the error was detected. The error may be caused by the absence of a token before the indicated token. And remember, this can be frustrating if you're looking through your code and you think, and it's telling you that there's an error somewhere, and you're like, there's nothing wrong with that thing it's pointing at. It's because it's pointing here because it's the first place where it realizes that there's an issue, that something was missing earlier, created the issue. In the example, the error is detected at the function print because a colon is missing right before it. There should be a colon after the true. File name and line number are printed so you know where to look in case the input came from a script. Exceptions. Even if a statement or expression is syntactically correct, it may cause an error when an attempt is made to execute it. Errors detected during execution are called exceptions and are not unconditionally fatal. You will soon learn how to handle them in Python programs. Most exceptions are not handled by programs, however, and result in error messages as shown here. Like if we tried to multiply 10 by this statement, which tries to divide by 0. Look at a zero division error. Or if we say 4 plus spam times 3, since we haven't defined spam earlier in the code, we get a name error. And here we've got a string 2 and the integer 2. And this can be addition if it's two floats, or it can be concatenation if it's two strings, but you can't concatenate to an integer, so can only concatenate string, not int to string. The last line of the error message indicates what happened. Exceptions come in different types, and the type is printed as part of the message. The types in the example are zero division error, name error, and type error. The string printed as the exception type is the name of the built-in exception that occurred. This is true for all built-in exceptions, but need not be true for user-defined exceptions, although it is a useful convention. Standard exception names are built-in identifiers and not reserved keywords. The rest of the line provides detail based on the type of exception and what caused it. The preceding part of the error message shows the context where the exception occurred in the form of a stack traceback. In general, it contains a stack traceback listing source lines. However, it will not display lines read from standard input. Built-in exceptions lists the built-in exceptions and their meanings. As you might expect. Handling exceptions. So it is possible to write programs that handle selected exceptions. Look at the following example, which asks the user for input until a valid integer has been entered, but allows the user to interrupt the program using Control-C, usually, or whatever the operating system supports. Note that a user-generated interruption is signaled by raising the keyboard interrupt exception. There's a name for that specific thing. So say, while true, try to set the value of this variable x equal to the result of showing the user this string, getting the input back from the user, passing that as an argument into the input function, and then passing the output of that as an argument into the integer function, making an integer out of what the user types in response to please enter a number. Try to do that, and if you succeed, then break. That's the end of the while loop. If you fail, in the case of a value error, except if you get a value error, you should print this stupid crap. Oops, that was no valid number. The try statement works as follows. First, the try clause, the statements between the try and except keywords, is executed. Bada bing, bada boom. That's the clause, the try clause. If no exception occurs, the except clause is skipped, and the execution of the try statement is finished. If an exception occurs during execution of the try clause, the rest of that clause, the try clause, is skipped. In this case, there's not much to skip, but if you had a whole row of instructions here, the second that it found an exception, it would move on to its except clause. Then, if its type matches the exception named after the except keyword, the except clause is executed, and then execution continues after the try except block. If an exception occurs which does not match the exception named in the except clause, it is passed on to outer try statements. If no handler is found, it is an unhandled exception, and execution stops with an error message. And a handler being just whatever is defined by your except clause. What except clauses do is they make exception handlers. Where that is your defined instructions for handling an exception of a given sort, you know. A try statement may have more than one except clause to specify handlers for different exceptions. At most, one handler will be executed. Handlers only handle exceptions that occur in the corresponding try clause, not in other handlers of the same try statement. An except clause may name multiple exceptions as a parenthesized tuple, for example. Except in the case of a runtime error, in the case of a type error, or in the case of a name error, and pass. A class in an except clause matches exceptions which are instances of the class itself or one of its derived classes, but not the other way around. An except clause listing a derived class does not match instances of its base classes. For example, the following code will print B, C, D in that order. Okay. First, a class is defined called B, which inherits from the exception class, making it into basically an exception. I'm still a little bit iffy about this. Then another class, C, is defined, which inherits from B. And finally, a class D is defined, which inherits from C. So this one big family tree with its root being the exception class. And for class in this list of our classes that we just defined, for each to iterate through this, and for each class listed here, try to raise that class. And if you encounter this exception, do this in the except clause. If you encounter this, do this that's in the except clause. And if you encounter this, do this in the except clause. And whichever one, it will, check all three. But the way that these always work is, the first thing that it comes across that fits is what will actually get run. So in this case, since we start at B, and B is exception, this one will run. It'll print B. Okay, B first. Then we go to C, and since C is also exception, inheriting from B, then it will print C. It will find the except C and print that. And finally, it will, with D, find except D. As all of these have been defined as as connected because they all inherit from one another. Still a little bit seems kind of odd to me, but all this stuff does. Note that if the except clauses were reversed, with except B first, it would have printed B, B, B. The first matching except clause is triggered. Like the fact that these are in this order is the only way that it was getting B, C, D out of it was by putting B at the bottom, putting C above that, and putting D above that. Because all of these would have been triggered if C found B first, because it inherits from B. And if D found B first, well, because it inherits from C, and C inherits from B, Then so all three would have triggered except B had it been at the top of the list. Now, when an exception occurs, it may have associated values, also known as the exception's arguments. The presence and types of the arguments depend on the exception type. The except clause may specify a variable after the exception name. The variable is bound to the exception instance, which typically has an args attribute that stores those arguments. For convenience, built-in exception types define the string dunder method to print all the arguments without explicitly accessing .args. So say we tried to raise exception, the exception class, with spam and eggs as associated values, giving arguments to the exception. And in the case that we find exception as an instance of exception, then we should follow these instructions in the except clause, which include printing the result of putting instance, which is just this, an instance of this, into the type function and printing that, so we'll get back just exception class. And doing this, printing the arguments stored in that instance, so spam and eggs, as well as printing just saying inst will just automatically print the arguments associated with it because of what they just said here, that it allows the args to be printed directly. It will also update the values of x and y equal to the arguments attached to that instance, meaning x will now become spam and y will become eggs, which is demonstrated by printing this, right? And this is also, I feel like I'm following it, and it might just be confusing because it is nonsensical code. Like, I don't see why anybody would do this in any circumstance, and I assume that that's not the point, it's just demonstrating something, right? But it's still so, like, nonsensical. I'm not sure what's going on. Just don't feel confident about it. The exceptions dunder string output is printed as the last part, the detail, of the message for unhandled exceptions. Base exception is the common base class of all exceptions. One of its subclasses, exception, is the base class of all the non-fatal exceptions. Exceptions which are not subclasses of exception are not typically handled because they are used to indicate that the program should terminate. In other words, they are fatal exceptions. They include system exit, which is raised by sys.exit, and keyboard interrupt, which is raised when a user wishes to interrupt the program, typically with Control-C, as we mentioned earlier. Exception can be used as a wildcard that catches almost everything. However, it is good practice to be as specific as possible with the types of exceptions that we intend to handle, and to allow any unexpected exceptions to propagate on. The most common pattern for handling exception is to print or log the exception and then re-raise it, allowing a caller to handle the exception as well. So say we imported sys, and then we tried to set the value of a variable we define of f equal to the result of opening a text file called myfile.txt. I'm sorry. And we also set the value of the variable s equal to the result of calling the .readline method on this file that we just named f, or well, the output of opening the file anyway. And we set the value of the variable I equal to the result of putting the readline output of f through the strip method. Turned that into an integer. Okay, we're going to try these things. And in the case, except if we encounter OS error as error, that we're defining that, we're putting the OS, we're saying this exception is now this variable ERR, right? In that case, we will print the string OS error followed by the exception itself in the form of this variable we call error. And except in the case of a value error, simply print could not convert data to an integer, and except exception, I get an instance of the exception class as error, or is that covering everything? Print an F string in which we've got two replacement fields where, we say first unexpected and then fill in one with, error, just whatever we got here, and a replacement field that will, when printed, show the type of it. And I think this was going on, right? I don't understand what's going on when you're trying to raise or putting exception, the whole base class of all non-fatal exceptions. I'm not sure. Is that just saying if it's anything else, we'll catch it? I might have missed something here, but well, I demonstrably did miss something. The try ... except statement has an optional else clause, which, when present, must follow all except clauses. It is useful for code that must be executed if the try clause does not raise an exception. For example, for argument in a slice of the argv of sys, which goes from index 1 to the end, for the args in that slice, try to set the value of the variable f equal to the result of passing in arg and the string r into open. What? Except OS error, print cannot open followed by arg, or else print that arg followed by has, followed by the result of passing the output of .read lines on f through the length function, followed by lines. So it's a, print the arg has this many lines, and then close the file. The use of the else clause is better than adding additional code to the try clause, because it avoids accidentally catching an exception that wasn't raised by the code being protected by the try except statement. Exception handlers do not handle only exceptions that occur immediately in the try clause, but also those that occur inside functions that are called, even indirectly, in the try clause. For example, we define a function called this_fails, which was doomed to fail. The function does only one thing: it sets the value of a variable x equal to an impossibility, thus dooming itself. And if we try and put in the try clause just the function call, try to call this function, in the case of a zero division error, which we will make equal to a variable error, print the string handling runtime error followed by the zero division error that we set into this variable. So what we'd get, handling runtime error division by 0, right? Obviously. Raising exceptions. The raise statement allows the programmer to force a specified exception to occur. For example, we raise name error with an argument that is the string hi there, and we press enter. If we just type this into the interpreter and press enter, then what's going to happen? Well, we will be given as if this exception really happened. We just have made this occur. It says name error followed by the string that we passed in as an argument. Now the sole argument to raise indicates the exception to be raised. This must be either an exception instance or an exception class. Okay. A class that derives from base exception, such as exception or one of its subclasses. Okay, I think that's starting to clarify it, right? If an exception class is passed, it will be implicitly instantiated by calling its constructor with no arguments. Raise value error without an argument without even parentheses is just the same as passing it without arguments in an empty parentheses. If you need to determine whether an exception was raised but don't intend to handle it, a simpler form of the raise statement allows you to re-raise the exception. So say we try to raise name error with this argument, and except in the case of a name error, we should print an exception flew by. How interesting. So yeah, I guess this would first print an exception flew by, and then the full error thing with this argument that we passed in here. That's interesting. Because we put this second little simple raise, huh? Okay, that sort of makes sense. Exception chaining. If an unhandled exception occurs inside an except section, it will have the exception being handled attached to it and included in the error message. So say we try to open a file called database SQLite, database.SQLite. Except, in the case of an OS error, we should raise a runtime error along with the statement unable to handle error. And what we actually get, first, the actual error, which we don't mention as a possibility in the except clause or anything, is the file not found error because there is no such file. And during the handling of this above exception, which we didn't define an exception handler for, is what it will say. Son of a gun? What the hell? I just saw my camera just disappear for 2 seconds. Anyway, it will say during handling of the above exception another exception occurred, and then it will give us the thing that we defined. To indicate that an exception is a direct consequence of another, the raise statement allows an optional from clause. So, say, exception must be exception instance or none. If we raise runtime error from exc, this can be useful. Yeah, from, okay, to indicate that it is a direct consequence of another. This can be useful when you are transforming exceptions. For example, say we define the function func, which will do nothing but raise connection error. And if we try and put that function call inside this try clause, try func, in the case that connection error as exc, raise runtime error along with this message from exc. This will result in first this traceback and connection error. And the above exception was the direct cause of the following exception, runtime error. Raising this as exc and then raising this from exc, defining it as being directly caused by. It also allows disabling automatic exception chaining using the from none idiom. So say if we try to open once more this non-existent file database.SQLite, except in the case of OS error, we should raise runtime error from none. So, there won't be any chaining here. We're just going to get runtime error. For more information about chaining mechanics, see built-in exceptions. User-defined exceptions. Hold on. Programs may name their own exceptions by creating a new exception class, and see classes for more about Python classes. Exceptions should typically be derived from the exception class, either directly or indirectly. Exception classes can be defined which do anything any other class can do, but are usually kept simple, often only offering a number of attributes that allow information about the error to be extracted by handlers for the exception. Most exceptions are defined with names that end in error, similar to the naming of the standard exceptions. Probably a good idea so you don't forget what they are. Many standard modules define their own exceptions to report errors that may occur in functions they define. Defining cleanup actions. The try statement has another optional clause which is intended to define cleanup actions that must be executed under all circumstances. For example, say we tried to raise keyboard interrupt. Finally, print goodbye world. We'll actually print goodbye world first, and then we'll get the whole traceback and everything in the keyboard interrupt. Because if a finally clause is present, the finally clause will execute as the last task before the try statement completes, since raise keyboard interrupt is in the try clause, right? The finally clause runs whether or not the try statement produces an exception. The following points discuss more complex cases when an exception occurs. If an exception occurs during execution of the try clause, the exception may be handled by an except clause. If the exception is not handled by an except clause, the exception is re-raised after the finally clause has been executed. An exception could occur during execution of an except or else clause. Again, the exception is re-raised after the finally clause has been executed. If the finally clause executes a break, continue, or return statement, exceptions are not re-raised. If the try statement reaches a break, continue, or return statement, the finally clause will execute just prior to the break, continue, or return statement's execution. And if a finally clause includes a return statement, the return value will be the one from the finally clause's return statement, not the value from the try clause's return statement. For example, we define a function called bool_return, which tries to return true, and finally returns false. If we call the function, we will get false, because we get this before the try clause is finished executing, and it's, I think it's too late now, after it's returned false, right? A more complicated example is if we define a function called divide with two arguments x and y, and we try to set the value of a variable result equal to the result of dividing x by y. Except in the case of a zero division error, we should print division by 0, or else print result is followed by the result. Finally, print executing finally clause. So it's like injecting somebody with radioactive stuff so you can see where it goes. If we call the function with the arguments 2 and 1, we'll first get result is 2.0, and then executing finally clause. If we put in 2 and 0 as arguments, which we know will trigger this exception, then we will first get division by 0, and then executing finally clause. But if we put in two strings that aren't handled by any exception, and they're just complete nonsense, we're going to get executing finally clause first, and then we will get a built-in error that we didn't define, a type error. As you can see, the finally clause is executed in any event. The type error raised by dividing two strings is not handled by the except clause, and therefore re-raised after the finally clause has been executed. In real-world applications, the finally clause is useful for releasing external resources, such as files or network connections, regardless of whether the use of the resource was successful. Predefined cleanup actions. Some objects define standard cleanup actions to be undertaken when the object is no longer needed, regardless of whether or not the operation using the object succeeded or failed. Look at the following example, which tries to open a file and print its contents to the screen. For line in the result of trying to open this file, print line and use nothing as the end thing. The problem with this code is that it leaves the file open for an indeterminate amount of time after this part of the code has finished executing. This is not an issue in simple scripts, but can be a problem for larger applications. The with statement allows objects like files to be used in a way that ensures they are always cleaned up promptly and correctly. So with the output of putting myfile.txt through the open function, with that as this new variable f, then for line in f, print line and with this end marker. After the statement is executed, the file f is always closed, even if a problem was encountered while processing the lines. Objects which, like files, provide predefined cleanup actions will indicate this in their documentation. So raising and handling multiple unrelated exceptions. There are situations where it is necessary to report several exceptions that have occurred. This is often the case in concurrency frameworks when several tasks may have failed in parallel, but there are also other use cases where it is desirable to continue execution and collect multiple errors rather than raise the first exception. It certainly gives you more information, right? The built-in exception group wraps a list of exception instances so that they can be raised together. It is an exception itself, so it can be caught like any other individual exception. So say we define a function called simply f, and we make a variable x, which is equal to just this exception group. We're making a list of these specific exceptions that we expect may be defined. Raise exception group with this little note and this variable in which we defined the list of exceptions that we want to make into an exception group passed into as arguments, right? So if we call that function, we get, look at this delightful little ASCII art answer. That's the prettiest looking error I've seen so far. Now if we just try to raise that function, if we just put the function call in a try clause, accept exception class, the class as e, print an f string in which we replace this little spot with the type of e, will output caught class exception group e. By using accept star instead of accept, we can selectively handle only the exceptions in the group that match a certain type. In the following example, which shows a nested exception group, each accept star clause extracts from the group exceptions of a certain type, while letting all other exceptions propagate to other clauses and eventually to be re-raised. Goodness gracious, that's a lot of indentation. So we define f again, which will raise a whole exception group. We got this little note, group 1, followed by this list, in which we've got OS error, got system error, and then nested in that we've got exception group 2 that's got OS error and recursion error. And look at this, that's just fucked up. And then, okay, so if we then put this function into the try clause of a try except thing, try f except star OS error as e, then print there were OS errors, except star system error as e, print there were system errors, we will get both there were OS errors, and then next there were system errors, and then re-raising, right? All of this. It didn't just didn't just return the first exception that it found and then skip the rest of it like it might have otherwise. Note that the exceptions nested in an exception group must be instances, not types. This is because in practice the exceptions would typically be ones that have already been raised and caught by the program along the following pattern. Say we have an empty list that we call x, and we've got a for loop for test in tests. Let's try to run test, except in the case there's an instance of the exception class. Is that how you would read that, right? Except if there's an exception, a non-fatal exception, therefore one that is part of the exceptions subclass, whatever, how you put that, as e, then we will append to the end of x e. And if x raise exception group with this message and the entirety of x. Okay. Enriching exceptions with notes. When an exception is created in order to be raised like a child, it is usually initialized with information that describes the error that has occurred. There are cases where it is useful to add information after the exception was caught. For this purpose, exceptions have a method add_note that accepts a string and adds it to the exceptions notes list. The standard traceback rendering includes all notes in the order they were added after the exception. So let's say try to raise type error, along with a little message, the argument bad type. Except in the case of exception, which this would, okay, so that would always go first, right? Or okay, except exception has E, then we can do the dot add note that accepts the string and adds it to the exceptions notes list, right? We'll add note this to the notes list of the exception, and we'll add this, and in this case we'll erase it. And if we hit enter, what would we get? First, we would get type error bad type, and then we would get these additional notes. Okay, right, yeah, okay. So both of these things end up being true and happening, basically, right? Because you try and try successfully to raise type error, but because that is also to raise any sort of error, a non-fatal error, is also the condition of an instance of the exception class being run across by the code. So both of these things would happen, right? That's why we're getting first type error and then the note originally included with type error and the two additional notes added in the except clause. For example, when collecting exceptions into an exception group, we may want to add context information for the individual errors. In the following, each exception in the group has a note indicating when this error has occurred. So once again, our old function friend f, we define as doing nothing but raising OS error along with the note operation failed. And we define an empty list called x again. And for I in range 3, 0, 1, 2, we will try to call the f function, except an instance of the exception class, which we'll set equal to E. We will add the note, the f string happened in iteration, with a replacement field which will be replaced on output with I plus 1, I being the point of the iteration through 0, 1, 2, right? Happened in iteration 0, 1, or 2. And we will append E, this, to the end of our empty list. And if we raise exception group with the string we have some problems and this list as argument, what do we get? Get this big ol' honkin' novel. And you can pause the video and read that in more detail if you want. I mean, I'm not getting paid for this.